The algorithm I'm using to implement my agent is Monte Carlo tree search. I think it is quite suitable for a complex game like Azul as they often have a very large search space. Using Monte Carlo tree search can essentially alleviate that kind of problem. As you can see here, this is quite a classical way to implement Monte Carlo tree search. It has a selecting method, expand method, a backpropagate, and simulation method. Uh, the Monte Carlo tree search can also return a local best answer at any time during its search. This kind of characteristic is quite crucial for our task as the computational time is very limited. The greatest challenge I have encountered during the implementation is tuning parameters. This includes the rewarding function and the selecting method. If I would have more time, I would like to further tuning the parameters to improve the performance of my agent.
Hi everyone, I'm Xinwei Qian. Let me introduce approaches to. As described on Wiki, our Q-learning has two versions, one based on traditional feature constructions and the other based on simulations similar to MZTS. Due to time constraints, I will only discuss the MZTS-based version that we use in the final competition. Firstly, we define a policy class which contains the action selection strategy during simulation. We have two strategies. One is completely random, and the other is select actions randomly from a subset of good actions. The policy class also includes functions for computing future rewards. We aim to minimize the unfinished lines on the game board. Additionally, we design reward for completing columns and stats, as they have higher reward. However, completing rows introduce uncertain risks at the end of the game, so we devise reward for columns and stats. Next, we have the main part of our agent, which is still based on Q-learning. We store the training parameter in a JSON file, which can be read when needed. The following is the core of our strategy, a function used for simulation. We let the two players take turns making moves until the game end, and then compute the scores for both players. Our simulation is based on Q-learning. This function takes a parameter for the number of simulations, which we use to adjust the parameter. We need to balance the accuracy and the breadth of our computation. We also use an action filter that returns two lists, good actions and bad actions. It also provides a score for sorting purpose. Since our algorithm cannot compute all possible actions, we focus on simulating the good actions as accurately as possible. The next function is for action selection. As simulations are time-consuming, we set two thresholds. If the time exceeds 0.75, we reduce the number of simulations, and if it exceeds 0.9, we stop the simulation and directly return the result. Finally, we have the main function. If it's not in training mode, we directly compute the best action. If it is in training mode, we update the weight. However, it is worth noting that this version of agent only uses the code framework I developed for traditional Q-learning. The final version didn't train the weight. That's all. Thank you.
Agent is implemented using breadth-first search algorithm. The core of this implementation is to define the goal states. Here, the goal states are defined as states which fill a new line compared to current state, as implemented by the function here. The details of this implementation are presented in the page Approach 3 of the project wiki. This method serves as the baseline and helps test the performance of the other two methods.